All right, exercises from section 6.5. This is the improper integral section. And so we got to consider this one. If it's divergent, write D. If it's otherwise, evaluate it. So we're going to see what is the problem child. Is it 0 or 3? Well, if we put 0 in here, we get division by 0. And so that's the problem child. So we change it to the limit as a approaches 0 and do the calculus on this, the integral from a to 3 of, see, this is 9, that would come out, and this is x times x to the 1/2, so that's x to the 3/2 in the denominator, so it's x to the negative 3/2. So to integrate that, it would be, I haven't done the limit, so I'm going to write limit, I'll move over here, limit as a approaches 0 of, the 9 is there, and actually it could come clear out of the limit, but we're going to have this. So I'm going to add 1 to negative 3/2, which will be negative 1/2, and I'll have to divide by negative 1/2, so I'll have x to the negative 1/2 divided by negative 1/2. That's the antiderivative of this, evaluated from a to 3. So that's limit as a approaches 0. And negative 1/2 will come up and be a negative 2, so I'll get negative 18. And this would go in the denominator, square root of x, evaluated from a to 3, so I get the limit, I still haven't done that, of putting in 3, I get negative 18 over the square root of 3, minus a minus, which is plus, minus a minus 18, so it's plus 18 over the square root of a. So I worked out this integral all the way through, keeping my limit. Now I'm finally considering the limit. What's going to happen if a goes to 0 in this fraction? Well, it's going to end up with a denominator of 0, and a fraction that goes with a denominator going to 0 explodes, and this would diverge. So they want us to put a D for a diverge. Okay, number 2. That's kind of small. Hopefully you can see that. Looks like infinity is the problem here. So I'm going to have the limit as a goes towards infinity of the integral 2 to a of 3x squared e to the negative 3x cubed dx. And I think we can do this one with a u sub. I'm going to let u equal negative x to the 3rd, that power. Then du would equal negative 3x squared dx. So this is going to become the limit as a approaches infinity of this integral that I'm trying to work on here. I'm only working on the integral, keeping this held. I have a 3x squared. I have e to the u, and I have du divided by negative 3x squared if I solve for the dx that I'm trying to replace. I'm still working on the integral, So I still have this limit that I have to do at some point. My pen's dying. Looks fine some of the time, and some of the time it doesn't. So the 3x squareds cancel. I have a minus, but it's e to the u integrated, so it's just going to be e to the u, but u was negative x to the third, and there's a negative, and this has to be evaluated from 2 to a, which would be the limit as a approaches infinity of, I'd put the a in first, so I get negative e to the negative a to the third minus a minus, so it's plus e to the negative 2 to the third. This is just a constant. It's not affected by a going to infinity. I am now working on this limit. That's a constant, so that's not a problem. But what happens with this as a gets really large? Well, it's e to the negative a, so that's an exponential that's going this way. Graphs like this. And if we let a get really large, this gets closer and closer. Oh, it's negative, so it's flipped over the x-axis, so it's going like this. But it's going to keep going closer and closer to 0, so this will approach 0 for really large a's. And so this comes out to be, this will go to 0, and this is all we get. So we get e to the negative of 2 to the third, so e to the negative 8. Switch pens. Okay, number 3. So, do we have an improper integral here? Yeah, I think we have a problem with going to negative infinity. So we're going to have the limit as x approaches, or as a approaches negative infinity of the integral from a to 2, negative 2, of e to the 2x over 1 plus e to the 2x dx. And I think a u sub on this might be useful. I'm going to let u equal 1 plus e to the 2x, that whole denominator. Du would be equal to, the derivative of e to the 2x is e to the 2x times the derivative of the inside, which is 2, chain rule, dx. And so I would divide by this to replace that. So I'm going to get the limit as a approaches negative infinity of the integral. We're going to have new limits here because I've got a u, so I'm just going to put question mark to question mark. And before I actually do the integration, I'm going to switch back to x's. So I have e to the 2x, and the denominator is what I let u be, and my dx is du over 2e to the 2x, and the e to the 2x's cancel, and so I have a 1/2 here that would come out. So I have, If I integrate 1 over u, I'm going to get ln u. So I'm going to have ln u in absolute value, but u is 1 plus e to the 2x evaluated, times a half because of that 2, evaluated from back to my original limits, because I'm back in x's, a to minus 2, and that would become the limit as a approaches infinity of, so I'll put in the minus 2, so I'll get 1/2 ln absolute value of 1 plus e to the negative 4. That's all positive, so I don't need the absolute value on that, but I do put it minus, and then I will have the 1/2 ln, and then I'm going to put the a in there, so absolute value 1 plus e to the 2a. And now I have to decide what's going to happen with this as a goes to negative infinity. I've dropped my negative someplace. Okay, so what does e to the 2a look like? Well, e to the x looks like this. E to the 2x would look just, it makes it half as wide. So it just makes it a little steeper like this. And I want to go to a negative infinity. So what's this doing as it goes towards negative infinity? Looks like it's going to 0. So the limit of this expression is going to be, this one's just a constant, is going to be 1/2 ln of 1 plus e to the minus 4. So that's going to be the value of this improper integral. Number 4. Now this one, at first glance, doesn't look like there's any problem. But we have to remember what 1 over x or 1 over v looks like. It looks something like this and like this. So there's an issue right in the middle of this interval. So we need to split this up into 2 pieces, or maybe do 1 and then double it. Or let's see, if we're going to do from minus 2 to 2 of 1 over v, this area and this area is going to cancel, because that's negative and that's positive, and so we're going to get 0 for an answer on this. But let's use the improper integral thing. So we would have to do this as the integral, the limit. Well, let's take this. Let's split this up into 2. It'd be from minus 2 to 0 of 1 over v dv plus the integral from 0 to 2 of 1 over v dv. And to do this one, we'd have to do the limit as the problem here is the 0, so as a goes to 0 of the integral from minus 2 to a of 1 over v dv plus the limit as a goes to 0 of the integral from a to 2 of 1 over v dv. Now, the integral of 1 over v would be ln v, and we'd put a in it, so we'd have the limit as a goes to 0 of, now these two can be put together, so I'm going to have ln absolute value of a minus ln absolute value of negative 2. That's doing this one. Plus, then I'm going to do this one. I'm going to have ln absolute value of 2 minus ln absolute value of a, and now I can simplify this a little bit before I do this limit. And the ln of a, if it was just this would explode because ln keeps getting bigger and bigger. But when I have these two, we have this negative area canceling the positive area. This one, which gets very big, is canceled by this one, which gets very big but negative. And ln of this minus, let's see, ln of minus 2 absolute value is the same as ln of 2. So we have ln of 2 plus ln of 2, minus ln of 2 plus ln of 2. Those two cancel, and we have 0. And as a goes to 0, 0 doesn't change, and we get the area under this plus this is going to be 0. From 0 to negative 2 to 2, we're going to get a total area of 0. This would diverge. But these two together, two diverging ones, actually are coming up with 0. Okay? All right, 5. Find the area under the curve y equals the tangent of x. So, what does the tangent curve look like? Well, the tangent of 0 is 0. The tangent of pi over 4 is 1. And the tangent of pi over 2 is an asymptote. And they want to find us from 0 to pi over 2. So they want this area. So the problem is at pi over 2. So we're going to have the integral with a limit as a approaches where it's an asymptote, pi over 2, of 0 from 0 to pi over 2, tangent t dt, they did it with t's, so we'll do it with t's. And so we get the limit, I'm not taking the limit yet, I've got to do this integral, of a approaches pi over 2, and the antiderivative of tangent, let's see what that happens to be. Antiderivative of tangent is ln secant of x. ln secant of t evaluated from 0 to pi over 2. So we're going to get the limit. We're not doing this part yet. Oh, excuse me, this was A. We had to put A in here for that. So this should have been A. Bad, 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 bad. That's got to be A because that's the problem. So that's got to be A. So as A approaches pi over 2, and we're going to put in A into this, and we're going to ln secant of A minus ln secant of 0. So now we have to remember what secant is. Let's see, secant is 1 over cosine, and so we've got to figure out what 1 over cosine of A looks like. Well, if A is going, let's see, we're not going to worry about that, so this is going to be ln, we got to still take the limit, sorry, get this all down here, as A approaches pi over 2, ln of 1 over cosine of A minus ln 1 over cosine of 0. So is this a problem? Let's see. Cosine of 0 is 1. ln of 1 over 1, ln of 1 is 0. So all of this is 0. That's not a problem. So now we've got to look at this as A goes to pi over 2. Well, cosine of pi over 2 is 0. 1 over 0 is very large. This part goes to infinity. And even if we take the ln of it, this whole part will go to infinity. And so this is going to diverge. Okay, 6. Looks like the problem is not E, the problem is infinity. And so, what do? So, we'd have the limit as A approaches infinity of the antiderivative, or whatever, of from E to A of ln x over x dx. If I let u equal ln x, du is 1 over x dx, and then I get x du equals dx, so this becomes the limit as A approaches infinity. The integral, new limits, because I'm going to u, ln is u, and dx is x du, and I have an x in the denominator. They cancel, so I get I get the antiderivative of u, which is 1/2 u squared, but u was ln x. So what does this turn into? And now we're evaluating it. I'm back in x, so I'm going to go from E to A. So I get the limit as A approaches 0 of, put in the A, and I get 1/2 ln of A minus, squared, minus 1/2 ln of E. squared. Well, ln of e is 1. So 1 squared is 1 times a half. This is just 1/2, this piece here. But what happens to this when a goes to 0? Well, ln of 0, remember the ln curve looks like this, so ln of 0 is negative infinity. Squared is a positive infinity squared, which is really big, explodes, diverges. Okay? Now this might not, because now we're dividing by even more, and so when we go to infinity, the area of this gets smaller and smaller and smaller, so that one will probably converge. We're going to have the same u substitution on this, so we're going to have this same stuff, so this is going to be the limit as a goes to infinity of the integral from, excuse me here, this one, integral of from something to something, because I'm going to u, and this would be x in the denominator, 1 here, ln is u, and dx is x du. The x's cancel. This becomes 1 becomes ln of u, and u was ln of x, and we got to figure out what is going to happen as a goes to infinity of this evaluated from, now I'm back in x, so I'm going to go from e to infinity. So I get limit as a goes to infinity of ln of ln of, oops, I'm putting a in here, of a minus ln of e. ln of e is 1, ln of 1 is 0. That's gone. And so I just got to figure out what this does. That goes like this, and then the ln of this is still getting bigger and bigger, and so this is going to go to infinity, so this is going to diverge. So it didn't get small enough, fast enough. Okay, I'm going to check myself on that one. I'm a little nervous about that one. Let's see here. Hopefully this won't take me that long to get it up on my computer here. I've got a lot of stuff up, so it might take a little bit of time. Let's go to here, go to improper integrals, and this is number 6, so go down here. Nope. Wrong place. Selected answers. 6.5.6. B diverges. So we got that one correct. A and B both diverge. We've got even more in the denominator now. So let's see what happens on this one. So let me get another piece of paper here. Again, we're going to do that same u substitution as we did up here. So let's see, position this. I should work about there. You can see that. So I'm going to have, the problem is the limit as a goes to infinity of the integral from e to a. That's the problem. So I'm going to replace that with an a of 1 over x ln of x squared dx. And these are all positive, so I don't have to worry about that absolute values, but I'll keep that there. So it's going to be limit as a approaches infinity of don't know what to don't know what when I do the u substitution. For ln x, we're going to have a u, and we're going to have that squared, and the dx is going to be x du, and I have an x down there that's going to cancel that x. And so when I integrate this, that's u to the minus 2. If I add 1 to this, I get u to the minus 1 divided by minus 1. So I get the limit as a approaches infinity of minus 1 over u, that's this integrates to this, evaluated from don't know to don't know, because that's u, so it becomes the limit as a approaches infinity of, this is 1 over u, which is ln x, so minus 1 over ln of x, putting in the old limits, a minus a minus, so plus 1 over ln of e. This part, as a goes to infinity, ln goes to infinity, and if the denominator gets really big, this will go to 0, and so we get this is all it's left, and ln of e is 1, so we have 1 over 1, which is 1. So this one converges. And the integral value is 1. And you can see that they had ln to the positive 1, then they have ln to the minus 1, and then to the minus 2. And what happens if it goes to even higher powers? Well, we're going to get ln of e underneath to a higher power, but this is just 1, and the x's are going to cancel out in the u substitution, and this will, if it's got higher powers of this is going to also still go to 0, so we're going to get this will always converge to 1. Oh, they said converges to 1p minus 1. 1 over p minus 1. I better take that back and let's actually do this one. Okay, same u substitution. You can see that up there. So I'd have the limit as a goes to infinity. We're going to do the antiderivative. Don't know, or it's supposed to be from e to infinity, but I'm making it a of 1 over x ln x to some power p dx. So if p is a positive real number, then we can do this one, I think. So we get if p is 1, it didn't work. It diverged. But if it's 2, it does work. So let's see what happens here. So if we make that u substitution, we get the limit as a approaches infinity of the integral, and we don't know to what no, because we're making a substitution, and we get for dx we get x du, which cancels the x, and then we have u to the p power, and the antiderivative of that is that's where it comes from. So we get the limit as a approaches infinity of the x's are canceled, and so u, that's u to the negative p, to integrate this, we add 1 and divide by that. So we get u, which is ln of x, to the, see, that would be 1 minus p over minus 1 minus p, evaluated from e to a. So we get the limit as a approaches infinity of, put in the a for x, so we get ln a to the 1 minus p over 1 minus p minus ln of e to the 1 minus p over 1 minus p, and 1 minus p is a constant. ln, if this would have to be in the denominator for this to converge, because ln grows without bound as a goes to infinity, so we need that to be in the denominator. So p must be greater than 1. If it's not, then this will be in the numerator. If it's greater than 1, we'll have 1 minus 1.1, which would make a negative exponent, but put it in the denominator. So p has to be greater than 1 for this to converge. And if it does, this will, if it is p is greater than 1, this will go to 0. And this ln of 1, ln of e is 1 to any power is 1, and we get out of this, the converging value would be 1 over 1 minus p times a minus 1, which is 1 over p minus 1. So this will be the converging value if p is greater than 1. And that's what they have for the answer. Good thing I took my time doing that one. Now they turn it around and say the problem is going to be 0. ln of 0 goes to negative infinity, and this goes to 0, so we have a problem there. So how do we do this one? So probably again the same substitution. So will be, can you see that substitution still? Yes, okay. So we'd have the limit as a goes to 0 of the integral from 0 of a to 1 of, I'm going to make the substitution, so I'm going to put question mark to question mark. If I let u be ln x, that's going to be u over the x, and dx is x du. The x's again cancel, and the integral of u is 1/2 u squared. So I have the limit as a approaches 0 of 1/2 u squared evaluated from something to something. Change it to x's, so we have the limit as a approaches 0 of 1/2 ln a as we go from back to our original, which was 0 to 1, and that becomes the limit, still not doing the limit, of 1/2 ln 1 minus 1/2 ln of, oh, this is a, 1/2 ln a. ln of 1 is 0, so this is 0. And ln of this, that goes off to the graph of ln, will go off to negative infinity when we get close to 0. So this goes to negative infinity, so this diverges. And then, how do we do ln of x? From 0 to 1. Well, you can probably guess that that's going to diverge too, because that goes off to negative infinity. But let's just check. Maybe I'm wrong on that. And the answer key says I am wrong on that. So let's do this one. I'm going to do the same substitutions. Actually, no. This one we have to do by parts. I believe. We're going to put ln x for u, v, f prime. So I take the derivative of this and I get 1 over x dx. And I put here just dx, and this becomes x to just x. 1 dx becomes x. So we get u, it's uv minus the integral of these two, so v u prime, and so we get, and I have a problem is at 0, so we have the limit as a approaches 0 of uv x ln x, and we're all in the positive area, so we don't have to put absolute value on that, minus the integral, we're still in x, so it's from a to 1 of these multiplied 1 over x times x, which is just 1 dx. And this becomes the limit as a approaches 0 of, this part has to be evaluated from a to 1 also. So if I put in 1, I get 1 ln 1 minus a ln a minus, now I integrate 1, which is just x, and then I got to put in 1, so I'm just going to get 1 minus, and then put in the a. Oh, sorry, that was off the screen. Sorry. So this, I put in the 1 and the 1 into both of them, then put the a into both of them, subtract that, and then I got minus this, the integral of this is x, so I put in 1 and a into x, which is 1 minus a. And now I got to look at this as a goes to 0. Well, ln of 1 is 0, so this is 0. If I put 0 times, well, 0 times ln of 0 probably is 0. As we get closer, 0 times ln of 0, that goes to infinity, that goes to 0. They're in a battle. I think that'll go to 0. This will go to 0, and we get negative 1. And I should do a little bit more to verify that. Let's see, how can I do that? To verify that, I have a ln a, and I'm trying to find out what the limit of that is as a goes to 0. So if I put the a in the denominator, as 1 over a, then if you remember L'Hopital's rule, when this goes to 0, this will go to infinity, and this will go to infinity, so I can take the derivative of both of these and see what that does. That would be the limit as a approaches 0 of the derivative of ln a is 1 over a, and the derivative of 1 over a, that's a to the minus 1, its derivative would be minus 1 a to the minus 2, minus 1 a to the minus 2, which puts it over a squared, and this a would cancel one of those, and we'd get the limit as a approaches 0 of, see, this 1 over a squared would come up as an a squared. That would be a. The a squared over a is just a, and we get a minus. And as a goes to 0, this goes to 0. So this does go to 0, and we get only the minus 1. And so the limit, this converges on minus 1. Surprisingly, even though this graph goes like this area in here on this ln x curve from 0 to 1 is only minus 1. Seems like it would go to infinity, but it doesn't. Okay. And finally, this one. Okay, so there's something we can do sometimes to compare integrals and know whether something converges or not. If we increase the denominator of this, we're looking at this one here. What happens to this as this goes to infinity? Well, this is virtually impossible to integrate. So even if we did the limit and said as a goes to infinity of the integral from 1 to a of 1 over 1 plus x cubed dx, without some really fancy mathematical abilities, this does not integrate very easily. But we know that it's got to be less than this, because if I take 1 and divide it by a bigger denominator than this does, a bigger denominator makes the fraction smaller, so this is always less than this. Therefore, if I were doing the limit, they used b, so I'd be doing the limit as b goes to infinity of this, it would be less than the limit as b goes to infinity of this. And this, if we integrate that, that's x to the minus 3. Integrated is x to the minus 2 over minus 2 is minus 1/2 over x times x to the 1 over the minus 2 is 1 over x squared. So minus 1/2, 1 over x squared, evaluated from 1 to b. We put in the b and let b go to infinity, and that part will go to 0, and we get minus 1/2. And this has to be less than that. And so then they say, look at this one. What's going to happen? Well, if we're in the positive values of x, this denominator will be bigger than this denominator. This does converge. You can do the math on that. X to the minus 2 in antiderivative is minus 1 over x. And then we go to infinity. That goes to 0. And so we just get minus 1. And so this has to be less than minus 1. And 1 over x, ln of x is always smaller than x This is always bigger than that, so this denominator is always bigger than that denominator, which makes this fraction always smaller than this fraction, and you can do the integration on that, and why must it be true that this diverges? Well, if it's bigger than this, and if you do the limit on this, you're going to find that that diverges, so this must diverge if b is going to infinity. If we're taking the limit as b goes to infinity, that's what we're doing on all these. Let b go to infinity. You can check this one out doing what we've done. That goes to infinity, so that must go to infinity because it's bigger than that. So we're supposed to check whether this converges or diverges. And so we're letting x go to infinity. We're not going to change this denominator, but we're going to look at this. So this is always going to be bigger than this. This will always be bigger than the integral from 1 to infinity of 1 over x, and I'll just take the 1 out, the square root of x to the 4th over x to the 4th. If I let that numerator is smaller than that numerator, so this has to be a smaller square root than this is. And x to the 4th over the x to the 4th is 1. The square root of 1 is 1, so this is gone. And 1 over x, like it here, this does not converge. It will diverge. Let's just go ahead and show that. So to integrate that, that would be ln x, and we'd be doing evaluating the limit as b goes to infinity of this going from 1 to b. So we'd have can you see that? We'd have ln of b minus ln of 1 when we put the limits into that, and ln of 1 is 0, but b going to infinity, ln goes to infinity, so this would diverge. This one diverges, and this one's always bigger than that, so it must diverge. Okay?